So let's have a look at wind instruments. How do opened or closed tubes produce different frequencies? Now, air within an open or a closed tube can be made to vibrate. So when I'm talking about an open tube, both ends are said to be open. Could be like a paper towel tube or a toilet paper tube. That's an open tube. A closed tube is closed on one end. That would be something like a test tube where only one end is open. So let's look at a tube which is open, and this will serve as our generic diagram. There's two ways of viewing what happens on the inside of a tube. We can look at the air being displaced, and that's the preferred view, or we could look at the pressure. Let's look at the displaced view first of all. So inside this tube we have air particles, and if we observe the individual air particles inside the tube as the tube is resonating, as it's vibrating, producing the sound, you'll find that the particles directly in the middle won't vibrate. So that constitutes a node. The particles on the end of the tube, however, vibrate the most. So as you move away, the vibration increases. So at the ends of the opening, both ends of the tube are open, we would consider that to be the antinode, and the middle of the tube would be considered the node, and that's where there's no motion occurring. So if we sketch what we imagine the wave looks like on the inside of the tube, it would consist of half a wave. We have essentially a quarter of a wave here and a quarter of a wave here. 2/4 is a half. That would constitute the fundamental frequency of the open tube. So that's in terms of displacement of air, displacement referring to the movement of the air particles, and that's the common view. Most textbook authors, most people who study wave motion of air in tubes usually take the approach of describing things in terms of displacement of the air particles. On the other hand, it's worth thinking about, well, what does the pressure look like on the inside? And we can still refer to this diagram right here. You would think that, well, if you're moving this particle back and forth quite a bit, we would end up getting compression and rarefactions in this region. So if you have a rarefaction, that means you have a low pressure, and this would be relatively high pressure. Hence, we would call that the antinode, the region of high pressure, and the openings, the node, regions of lower pressure. Again, this is the preferred view, and this is the view we're going to continue on in this course. So let's look at open tubes first of all. And open tubes are very similar to the physics of a string. In a string, we would have nodes on either end of the string. For an open tube, on either end, we have antinodes and a node in the middle. The length is equal to half of the wavelength, or the wavelength is going to be equal to 2 times the length of the tube, and that would be for the first harmonic. So L is equal to 1/2 lambda for the first harmonic. And if we incorporate the speed formula, velocity is equal to the product of frequency and wavelength, we end up with this formula, F1 is equal to V divided by 2L. And that should be familiar because that's the same formula for the first harmonic of a string. Remember, tubes, open tubes and strings have the same features. The fundamental is equal to half of the wavelength. Now if we look at the second harmonic is going to consist of an antinode on the openings, both openings of the tube. In the middle there's an antinode, and in between we have the 2 nodes. And if we count all the sections here, that will show us that L is equal to the wavelength of the second harmonic, or the wavelength of the sound. So the frequency of the second harmonic is simply equal to the speed divided by L. The second harmonic is also known as the first overtone, the same type of nomenclature that we use for describing strings. Now the third harmonic, I don't have that written here, but this is the third harmonic. We would have antinodes again at the openings, and then a series of nodes and antinodes in between. Now what I've added to this diagram, it's worth looking at all of these in terms of the quarter wavelength. How many quarters of a wavelength or quarters of a wave do we have? So if we go back to this one, you see that this constitutes a quarter, and this constitutes a quarter, and 2 quarters is a half, hence half lambda. Here we have a quarter. If we subdivide this, we have a quarter here and a quarter here, and a 4th quarter here. So 1, 2, 3, 4 quarters is equal. 4 quarters is going to be equal to 1, of course. The last example here, we have a total of 6 quarters, and 6 quarters is equal to 3 halves, hence 3 halves in the formula. Okay, this will become useful, more useful when we start talking about closed tubes. Now to summarize the formulas for open tubes, it's the same formula that's used for strings, where if you want to know the frequency of any harmonic, n, that's equal to the harmonic number times the velocity of the wave divided by 2L. And another view, you know that the harmonic frequencies are whole number multiples of the fundamental frequency. Some examples of open tube instruments would be wind chimes or chimes, a flute, a recorder, any sort of a wind instrument where you're blowing air through a tube, and the end of the tube has an opening. So that would be something like a trumpet. A trumpet has what's called an exciter, the mouthpiece, where you're producing one frequency, and the sound is dependent upon, maybe a trombone would be easier to explain. When you operate a trombone, you're changing the length of the trombone, and that, of course, is going to affect the frequency because we see that frequency is dependent upon the length. In playing in a trombone, please understand that playing a trombone is not limited to just changing the length. That would be too limiting. So a trombone player also changes frequency with their own lips. So musical instruments, there's a lot of talent there because not only you're relying on the basic physics, but you're also relying on understanding how to maximize that physics, maximize the frequencies that you can produce. A bugle is a simple horn wrapped around so you can hold it. And all the notes are played by adjusting the vibrations of your lips, and that passes through that long tube. Now, closed tubes, there's a little more to closed tubes than open tubes. A couple of things you need to be aware of. Let's start off with the fundamental, or the first harmonic. The difference here is that one end is closed, and at the closed end we always are going to have a node. That's always true for all of our examples. Always have a node at the closed end. Now the opening for the first harmonic, it's very simple. There's an antinode, and if you look at what is the minimum that can fit into that tube, the minimum happens to be a quarter wave. Quarter wave gives you a node and an antinode. So that means that the length is equal to 1/4 of the wavelength for the first harmonic. So if we add the velocity equation to this, we end up with frequency of the first harmonic is equal to the wave speed divided by 4 times the length of the tube. Now if we go to the second harmonic, we're not going to hear any sound in the second harmonic. The second harmonic actually doesn't even exist. I've drawn it just to prove a point. We know that the closed end has a node, like all of them. I mentioned that earlier. And what we're doing is harmonics are always whole number multiples of the fundamental. So all of these are going to be multiples of this fundamental right here, multiples of a quarter. So this would be the second harmonic, so it would be 2/4. The problem is, if you have 2/4 inside a tube, look at what's on the opening. The opening has a node. Therefore, this tube will not resonate with twice the frequency. So there's no sound. That tube cannot produce double the frequency of the fundamental. So second harmonic does not exist. Now, that is always going to be true for every even number harmonic. So even numbers don't exist. Closed tubes only produce odd harmonics. So the rest of the diagrams, I've only drawn odd ones. No point of repeating this idea. So here we have the third harmonic. The third harmonic is going to be 3 times the fundamental, so 3/4 lambda. So the frequency of the third harmonic will be 3/4 V divided by L. And if we jump to the next odd harmonic, that'll be 5. So 5 times 1/4. So 5/4 lambda 5. So the frequency of the fifth harmonic will be 5/4 times V divided by L. So the formula that summarizes a closed tube is going to be the frequency of any harmonic is equal to the harmonic number times the velocity of the sound divided by 4L. Remember, open tube, you're dividing by 2L because you can fit half of the wave in the fundamental. And for closed tubes, you can only fit 1/4 of the wave for the fundamental. So the formula is slightly different, so you need to watch out for that. Now, some examples, panpipes that you're blowing. There are 2 types of panpipes. There are closed bottom or closed end panpipes, and there are panpipes that are just essentially tubes like straws which you blow across the top. Pipe organs, a pipe organ actually uses a combination of open and closed pipes. So I just want to emphasize that you can have one or the other in that type of a musical instrument.